Mean value theorem. Road trip! You're on a road trip with friends. At noon, you collect a ticket to enter a toll road at mile marker 1. The posted speed limit is 55 miles per hour, but you see no police. At 2 p.m., you exit the toll road at mile marker 141. When you hand the attendant your toll ticket, they respond with, "That will be $5 for the toll and $125 for the speeding violation." But wait, you didn't see any police cars or speed cameras. Were you speeding on the toll road? And if so, how did the attendant know? Well, from noon to 2 p.m., the car was on the toll road, which is for 2 hours. In that time, it traveled from mile marker 1 to 141, which is 140 miles in 2 hours. This means the average speed had to be 70 miles per hour. In order to travel that distance in that time, at some point, the car must have been traveling faster than 55 miles per hour. Therefore, it must have been speeding. This concept led to the discovery of another major theorem in calculus called the mean value theorem, or capital M, capital V, capital T for short. Simply worded, the theorem states that if a function is continuous and differentiable on a given interval, then there exists a point in that interval where the instantaneous rate of change, or the speed at any moment of travel from the road trip, will be equal to the average rate of change, or the average speed of traveling during a road trip. This results in the tangent line at that point being parallel to the secant line through the endpoints of the interval. Formally speaking, suppose f of x is a function that satisfies the following. F of x is continuous on the closed interval from a to b, and f of x is differentiable on the open interval from a to b. Then there exists a number c within a and b such that f prime of c is equal to f of b minus f of a over b minus a. Now let's try an example with using the mean value theorem. Find the value c which satisfies the mean value theorem for the function f of x is equal to x squared on the closed interval from 1 to 3. Similar to Rolle's theorem, we first must check that the mean value theorem can be applied. So first, is f of x a continuous function on this interval? And the answer to that is yes. It's a section of a parabola, completely continuous on the closed interval from 1 to 3. And the next question is it differentiable on the open interval from 1 to 3? Yes, it definitely is. Again, because it's a parabola, there is no corner, cusp, or vertical tangent that exists there. So because these conditions are met, now we can apply the mean value theorem. The next step is to find the slope of the secant line of the endpoints. And the reason we're doing that is because the mean value theorem states that the derivative at some point c is equal to the slope of the secant line when evaluated on the closed interval from a to b. So that's f of b minus f of a over b minus a. So we have to figure out what the numerator and denominator are going to be on the right-hand side of this equation. So if we do that, we're going to fill in f of 1 and f of 3. Well, 3 squared is 9, 1 squared is 1. So we have 9 minus 1 over 3 minus 1. So we'll have 8 divided by 2, which is equal to 4. So again, we took care of what this right-hand side of the equation is going to be. The next thing that we have to do is determine what the derivative is. Well, the derivative of x squared is going to be 2x. And then we set this 2x equal to the slope of the secant line, replace x with c, and solve for c. So 2c is equal to 4. So c is going to be 2. And that's the final answer to this example problem. C is equal to 2. Here's another example for the mean value theorem. Find the value c which satisfies the mean value theorem for the function f of x is equal to x raised to the 2/3 power on the closed interval from -1 to +8. First, we need to see if the mean value theorem can be applied here. And the first question is f of x continuous on this closed interval from -1 to +8? Well, the answer to that part is yes. it is continuous on the interval. Now the question is it differentiable, or are there any cusps, corners, or vertical tangents? And making it not differentiable, well, in this case, there is. This function, x raised to the 2/3 power, will look something like this when you graph it. You've got that little corner or cusp as it approaches 0. So therefore, because that occurs at x equals 0, mean value theorem cannot be applied.